Good morning. Welcome to ECE 441A, 541A. If you were looking for a visual, if you're one of the online students, you're just going to see a screen. That's probably a good thing, and you won't have to look at me. For those of you in class, welcome. Hopefully you had a good summer. My name is Hal Tharp, and we will be working through a topic called automatic control, and we will probably fill up this lecture hall, if not today, during exams, or I hope that everyone shows up for the exams, and we'll go over those dates or planned dates as we work through this material. This is typically how I will begin a class. I'll have the announcements displayed for a little bit before class begins. And today what I need to do is some business just to make sure we're all present, and I haven't included the name of the class, but I'll fill that in later. You are either in, well, I better do it now because you are in one of two sections. You're either in 441A or 541A. If you are in the class, you're registered for the class, you need to sign attachment number 2. There's going to be many, many sheets floating around, so I'm going to see how well you follow instructions on the first day of class. Who knows which one you will see first, but if you are in 441A and you are already enrolled, sign attachment 2. I haven't even started to pass around attachment 1. You know what? To save you guys, if you want to add the class, come see me after class. That way it won't be quite as confusing. What you have to do is simply sign into the appropriate sheet. It will say either 541A or 441A, and try to pick the one that you're in. If you sign the wrong one, just next to your name put, 441A if you signed up on 541A. It's not that big of a deal, okay? I just want to see who is here and if we are able to sort of track students and classes. The other thing that you will be doing to begin with, so that I start to put a name with faces, I recognize some of you, quite a few of you, I guess, and I've seen others walking around. Don't ask me a quiz today, but I will maybe be quizzable after you've completed the passport assignment. The passport assignment is really your ticket into this class. It gives me a way of putting a picture of you with your name, and if you are Tom officially, but you like to go by Bill, Bill is your nickname. So write Bill as your nickname, and I will call you that. An email, something that will stand out from your classmates. Oh, I enjoy 320A. That's probably not very unique. Well, maybe it is. Maybe everybody else didn't like 320A, or maybe you like something else, but something that's maybe outside of engineering that will help me remember or put your face and name and some unique talent that you might have or some hobby that you enjoy. That's usually helpful for me to remember. Then, how do you like to learn? Whether this means anything or not, I don't really care. What I want you to be aware of is different strategies that you can employ. Not that you're one learning style or another. That's not so important. The important thing is that you're aware of different ways of trying to assess material and understand material, and finding ones that click for you at particular points in time. And some might be more effective one day versus another, but if you're aware of different strategies, that's what I'm looking for, and hopefully that will help you become a better student. Then there's a new book out. It was just published, A Mind for Numbers. and that should describe all of you, but maybe it doesn't. This is a faculty member now, and it says, A Mind for Numbers, How to Excel at Math and Science Even if you Flunked Algebra. So there's some interesting tips in here, and I would like for you to access her website and look at 10 good studying tips and 10 bad studying rules, and write up a little bit as far as what you connect with on the good and maybe what you've done in the bad that you'll try to avoid doing in the future for this class. Again, just little things that I'm hoping will allow you to be more successful in this class. And then I'm asking for your signature if you submit this via the Dropbox, which is what I'm expecting. So I need to, when I get back into the office, I'll try to put this on D2L. You can then download it, fill it in. You can just type your name. You don't have to worry about signing it if you don't have any way of scanning the finished document. I'm going to assume that when this document comes into your Dropbox, that that's representing your work, since that's you in the Dropbox. That's the passport assignment, and when did I say that was due? Ooh, probably right after the game. Isn't there a game Friday? Come on. So this is the fall semester. Football is now happening, and so maybe that's a good thing, maybe that's a bad thing, but I kind of enjoy the fall. It usually is a little cooler after the first month or two, and it's a nice time of the year. Where was that? Oh, that's to remind you that Fridays will be fun in here because we have to get ready for the game. In general, the games might be on Saturday. That's okay. We still have to do our run through on Friday, and that's what we'll be doing here. And most of our exams will be on Friday. So instead of being tested on the field on Saturday, you'll be tested on Friday and here 3 times during the semester. I don't think our final is on a Friday. Homework 1. Has everybody completed that? Show of hands. For you online students, you can just kind of give me a fist pump or whatever it's called into your screen. Let me know that you're there. But it's not available if somebody's already finished it. You can give me the solutions and then I'll post which ones you worked. No, that will be forthcoming, but again, that's due on a Friday in a few weeks from this Friday. Prerequisite quiz, I haven't decided when I will do that. I might actually do that online. I might have you fill that out online, and I might just say you're on your honor not to go looking up things while you're completing it. I can't check that, but I'll just trust you to sort of give me an idea of where you're at right now, and that might test some of your skills or some of the things that we need to look at in this class that maybe you haven't had the opportunity to look at, or maybe it's just rusty. So stay tuned on the prerequisite quiz. Today we have 2 main goals. One is to just walk through the syllabus, give you some feel for what's expected of you in this class and the process. All of this stuff, all of the material for 441A, 541A will be on D2L, most of it. It's got to be because we have some people that aren't in class, they're taking it online. So you need to shake their hand when you run into them. Won't happen. I was going to say, everybody turn to your right, turn to your left. Remember you did that. Did you guys get that in your first orientation? And they said you wouldn't be here, or 2 of you won't be here. Well, that's not the case, is it, anymore? So if you're online, you can look in the mirror and wave to yourself and say good luck and congratulations. Hopefully you're all in a good position now, and you'll enjoy this course, which is now after all of your core material if you're an undergrad, and it may be a class that you didn't see as an undergrad if you're in the 541A class. Syllabus. Did I introduce myself? Yes, no. Okay, people are really paying attention then, aren't they? That's my name, Hal Tharp. I'm I'm several places in the ECE building, but you'll find me on the 5th floor during office hours. And the office hours are scheduled in the morning. If that doesn't work for you, let me know and we'll try to make a connection with answering your questions. But we'll see if these work. They're right after class on Wednesday and Friday. Wednesday it goes a little bit longer. It's 9 to 11. And on Thursday we'll have an office hour from 11 to noon. And if that's not going to be consistent with the majority of everyone's schedule, then we'll change that. This class has now been modified. I don't know if you're aware of that, but I used to have a big podium right here, and I could stand between, that was between me and you. I kind of felt comfortable behind that desk. Now there's a camera, and I'm not going to turn it on, but I could be, on video. Oh, this can go down. Now you can really see. And this is now a portable or a movable station. Now somebody had that probably positioned just right so that they could lecture on the whiteboard, and I messed it up. Oh well. They'll have to learn some control and understand how to control that desk. Where were we? Course description, justification, teaching philosophy. You can read that later. There is a textbook. There's 2 textbooks. One has a brightly colored wing on it, and it's the 12th edition of Dorff and Bishop. Has anyone had any luck obtaining that in the bookstore or online? And if you have an earlier edition, obviously there's several editions. This is the 12th, and I think they're getting ready to produce the 14th. Can't count, can I? The 13th edition. Oh, they're skipping the 13th, just like the floors in a hotel. You ever been located on the 13th floor of a hotel? Probably won't find one. Goes to 12 to 14, so I was guessing that's maybe what was happening with this textbook. I don't think so. If you have an 11th edition or a 10th edition, it's probably fine. A lot of the core material, the question or the problem sets might be different, or they might be numbered differently, and so you'll want to make sure that you're working the correct problem that will be assigned or coming from the 12th edition. If you're in 541, there's another textbook, and that is available as a PDF online, and you don't have to purchase this. You can buy one if you want, but you can just obtain the PDF version, and the address for that is on the syllabus, which is included here. And if you're an undergrad and you want to read that, that gives you a little bit more theoretical background and a little different perspective on the material that we'll be learning in this class. As I said, I'm planning 3 exams. These are the tentative dates: September 26th, October 24th, and November 21st. Alarms are going off with the exam announcements, right? But hopefully you'll be well prepared. This is a little bit maybe confusing. The homework for the graduate students will be worth 5% of your grade because you have a project. If you're an undergraduate student, you will get 10% on the homework. We will have laboratories, physical laboratories. You'll go over to the ECE building. I'm working with the online students. You don't have to purchase 3 airplane tickets to fly here and perform the labs. Maybe I'll go into the lab and do or get the data and provide you as an online student with the data, and then you can work with it from there. Or you can tell me how you want to design your controller. These are the tentative dates on the labs. It would be nice if you read over and understood each of the labs prior to the appropriate exams. But the labs aren't due until the week after the exam. Just so you're not stressing about the lab before the exam. But I do want you to understand that material. That material is important for success on the different exams. Meaning exam 1, you'll want to have completed lab number 1, ideally. At least you understand the material, and maybe you can perform the lab after that first exam and turn it in. It's due a week after the exam date. Everyone will be doing the labs. We may do those in teams just because we have a fair number of participants in the class, and we only have one right now mechanical system. This is an ECE class, and we have you do control theory in the lab on a mechanical system. But one of the reasons for that is mechanical systems go a little slower than electrical systems, and you can physically see the response. If it was electrical, you're going, did it work? Did it happen? And you might not be able to see that much change. With the mechanical system, it's slow enough that you can actually see that movement and the result or the impact of your design, your controller designs. The final exam is December 17th. Does anyone have a calendar? I think that's a Monday, but don't hold me to that. It's a Wednesday. Okay, Monday's my other class. Okay, so it's a Wednesday, and I think, that might be the last day of finals. And it's 8 a.m. to 10 a.m., so you don't have to get up any earlier to get here for the final. Well, sometimes you do. You have a class that meets at 9:30 and the final's at 8, and you go, oh, I have to. But this one, you'll just be always getting up for an 8 o'clock class. It's a good thing. You'll be gainfully employed in a semester or two, and you'll be maybe having to get up and go to work by 8 a.m. Here are some of the topics that we will be discussing in this class, and I've tried to key those in. They pretty much go linearly down through the semester relative to which one is associated with the different exams. And you can read that later. And then the 4th page of the syllabus is a little bit more detailed, and it now correlates the homeworks with the topics that you will be needing. And I have to now assume certain topics are familiar with you or to you. If you didn't take 320A here at the University of Arizona, you can maybe find that material here and correlate that with what you've taken elsewhere and see if you're prepared, or I may provide that background material for you to work on your own, and it'll be on D2L to get you up to speed. There are several of those sprinkled throughout that I'm assuming that you've had from earlier coursework. For example, the final value theorem is somewhere here. State space representation, transfer function descriptions. Those I'm assuming you're somewhat comfortable with from 320A. Any questions on the syllabus, the process, the organization of the class? Let's then get started. This is a class called Automatic Control. And it really, you could think of it sort of separated into three different parts or pieces. We're going to start this topic, or it begins, with modeling. And that may be, well, we'll get into the modeling aspect in a minute. Then we will develop ways to analyze these systems that we've modeled. Meaning, once we have the model, it's going to then move into analysis. How do we analyze this? What's certain characteristics or properties of the system that we've now modeled? And maybe we're not happy with the way the system is behaving. And for that reason, we want to change the behavior of the system, and we'll do that via the design process. We'll design systems, subsystems, other blocks, other transfer functions, other differential equation related systems in combination with the original system to make the combination behave the way we want it to behave. That's the idea of control. We'll have a couple of ways of modeling. Which I'm referring to as methods of modeling. One is based on the physics of the system. And we will do more than just electrical modeling. We're going to have to worry about Newton. F is equal to ma. We'll have some mechanical systems. We'll have some electrical systems, and we'll combine those into electromechanical systems. And we'll start modeling all of those, and that will then give us a little bit more, a richer playground to play on to analyze and design with those systems. In electrical, we'll have our buddies. Everybody remembers Eli the Iceman. That's simply the current voltage relationship between inductors and capacitors, and this is in the time domain arena for that. So we will then look at a given system. Maybe it's an interconnected mass spring damper system. We'll have to figure out, how do we model that? How do we develop the differential equations to describe that? Or you might be given a circuit, an electrical circuit, and using these fundamental relationships for R's, L's, and C's, we won't get too fancy. Maybe we'll have some op amps to give us some gains, etc. But now we have this system that we can describe either in transfer function form or in differential equation form, all based on the physics of that system. Another method of modeling that we will employ here is a more indirect approach, and that's based on system identification. Meaning, we may actually go into the lab, which is what we will do, and you may excite the system. You may hit the system. You may don't kick the system, but you are going to push this mass with a driving force. And that might then initiate a response. And based on that response, what you can find are different characteristics of that system's, let's say, position. Maybe that's y. Y of t might be the position of a mass. And we might have then this t sub p, the peak time. Or we might say, oh, this is now our settling time, t sub s. Or we might have the ability to measure the percent overshoot. Those taken together will now allow us to identify the system in the form of a transfer function g of s. Meaning we might say, oh, that behavior looks like a second order system. And we can now create a transfer function g of s that is modeled by, or that describes, a second order system. And now we have to essentially fit the parameters or identify the parameters in this transfer function g of s. And maybe we will or will not be happy with the behavior, and that's why we're then moving on in the semester after the analysis, or after modeling and doing the analysis, to design a controller for that system. Or another way of identifying a system, which I'm going to say, know how to do, if I gave you the frequency response, the magnitude, can you then provide me with the transfer function g of s? And if you can't, you need to start thinking about how you would do that. What's happening right here at this first point, which I guess if you're online you can't have any idea what I'm pointing to. So what if we were right there and I said, is something happening there? It looks like it from the picture. Can you tell me what's happening at that location? There's a pole, isn't there? Depending on the slope, there may be one pole, two poles there, or at least a net pole behavior at that location. And if the frequency axis is provided on that plot, let's say as a function of omega, then you can identify where that particular pole is located in the frequency, for its frequency. And then you would have another pole or break out here. And if your system is minimum phase, then all you need is this magnitude plot to identify g of s. Do you remember what minimum phase means? I know it's been a long time. Maybe you've had a summer. You've had more than that in terms of semesters. But minimum phase means that you have all of your poles and all of your zeros in the left half of the complex plane. That provides a unique mapping between the magnitude response and your transfer function g of s. Minimum phase means, typically if somebody says, oh, your system is minimum phase, that means that you have all of your zeros in the left half plane. If your poles are in the left half plane, is that a good thing or a bad thing? Or do you remember? Do you even remember what I'm talking about with planes, left half and right half? I'm now in the S domain, the complex S plane, and if I am looking forward like you are, the left half plane is a good thing because there all the real parts of your poles have negative values, and that gives you this exponential decay that you need to have stability. Stability is based then on having your poles in the left half plane. And we may not begin with a stable system. We may have an unstable system, an inverted pendulum, and we want to stabilize that. Or a bicycle. How many rode their bicycle today to class? That's a good control problem. As long as you're moving forward with enough velocity, it's pretty stable. Maybe we'll get into some pictures of bicycles or designs of bicycles that are a little more interesting, and you can then figure out what are their dynamic characteristics based on the model of that bicycle. But a bicycle actually is a non-minimum phase system. It has a zero in the right half plane. We'll get in maybe more of that later. That's the first third topic-wise of the class, is modeling. We can do it from physics, differential equations, transfer functions, or we can do it indirectly via system identification in the time domain or frequency domain. That's what you want to be getting comfortable with. The second piece of the content is our analysis piece. And we will be playing in both domains again, or you should be starting to get very comfortable moving back and forth between the time domain and the frequency domain. In the time domain, you could be thinking differential equations. And as we said before, if we're analyzing a system, maybe we have its response as a time domain trajectory. And we can identify then the value of the peak of the output and when that actually occurred. We can also go out and find where it reaches a steady state. Why steady state? And the time it takes to get to, let's say, within 2% of that steady state value is our settling time. And do you remember, if we just had a first order system, this is not a first order system, this one's ringing, it has some oscillations, it's a second order system. But if we had a first order system, do you remember the relationship between that system's time constant and the settling time? 5, isn't it? 5 time constants will get you actually, so this is where you kind of have to look at the book and go, what? He's saying 4. What? I thought I grew up learning 5. What's the deal? 5 time constants get you within 1%. 4 time constants get you within 2%. Dorff may use the 2% settling time, so it might be 4 time constants. So you just have to sort of, and you can write that down. I'm assuming 5 time constants in my settling time. And then if you were physically measuring this, you would go out until you obtained the time interval in which you were within 1% of your steady state. If you're using 4 time constants, you would look out in time and say, oh, I need to just go out as far as I need to until that response gets within this 2% tube of my settling, or my final value. So just pay attention. I may be saying 5, the textbook might be saying 4, other textbooks might say 4.6. It's just what we decide to use. 4.6 is more accurately 1%. 5 is a little bit beyond 1% in terms of time. But we're doing things sort of back of the envelope in here. We need it to be fairly robust, our design. And so we can't really worry too much about 4.6, 4.5. If it's working the way you want it to work, it's going to be probably okay if you're using 4 or 5 and you're doing it properly. But T sub P is our peak time. That will be related to certain properties of the system. T sub S is our settling time. And as we said before, we might be using our percent overshoot if we have a second order system to give us some indication as to the damping in our system. If it rings a lot, we don't have a lot of damping, and we maybe have these poles very close to the imaginary axis relative to their, let's say, vertical distance. So they may be very close to the imaginary axis, and that might be then causing them to oscillate, and they now maybe have more vertical distance than they do horizontal distance in the complex plane, S-plane. We can also do our analysis in the frequency domain. In the frequency domain, you might be thinking transfer functions. And now Bode plots are your friends, meaning you need to get very comfortable with those frequency response behaviors. We'll talk about stability. We'll introduce a new way of working in the complex S-plane. I think you've already seen poles and zeros or pole zero diagrams, I'm assuming, from earlier courses. Let's say that's now this S-plane. We will learn something called the root locus, and that will tell us how the poles will, the closed loop poles, evolve as we adjust the gain in our system. And the root locus then, in this particular case, might do something like that. And maybe that's not what we want. Meaning if we cranked up the gain a lot in this system, our closed loop poles are going to migrate over into the right half plane, and we'll have an unstable system. Maybe not the best situation unless you're trying to design an oscillator. And then you might want to have something very close to the imaginary axis. Once we have that established, the modeling and the analysis, now we will want to get into the controller design phase. And one of the classic interconnection structures that we will have, this might be our plant. And now I have to draw it as a green. If you have somebody that's not familiar with engineering and you start talking about plants, what are they going to think about? A flower, a tree. We use plant to mean this system, G of S. So you may have some explaining to do when you go home and you start talking to mom and dad about plants. Oh yeah, I'm controlling a plant. Why do you want to control a plant? It looks fine the way it is. These flowers are not, no mom, it's not flowers that I'm interested in. It's this mechanical system. Well, why are you calling that a plant? It's the terminology that we have. So we now have a plant that we've now modeled and analyzed. Maybe it's not behaving the way that we want, And for that reason, we want to design a controller to improve the performance or the behavior of the system. And we probably are not going to just have that in a open loop configuration. We will actually measure that output and compare that with our reference. This was supposed to be a lowercase r. Maybe I should. That's our reference input, and the ideal thing, once we've designed D of S, would have this error signal being 0. Now, where we want it to go, if we're controlling a car, and that's now the speed, R, that we want to achieve, if it's now 55 miles per hour, we would like our car to reach that and stay stuck on that 55. In terms of these controllers, we will allow for many different ways of designing those and building those. Our analysis might be starting with the root locus, and we say, I don't like the way those poles are patterned in the complex S-plane. I want to shift those or move those around. We'll design a controller to modify those. You might have frequency response behavior or Bode plots, and you say, oh, the phase margin is not what I want it to be. I need to improve the phase margin. Well, how do I build a controller to make that happen? Or we might have a state space system, and we want to analyze and control the system in a state space environment. With the root locus and the Bode plot, we're in the frequency domain, and a very basic controller might be a first order controller. First order meaning the denominator of this transfer function has an s to the power 1. We have one pole. We might introduce a pole, a p, we might introduce a 0z, and we might adjust the gain k. And now, to sort of give us something to think about, now you're designing or creating this controller. And if you enjoy cooking, this is what you want to be thinking about, the analogy. Meaning you might want to spice up your, or make your system perform better by adjusting the spices. And here your spices are Z's and P's. So you have a Z shaker and a P shaker, and you're sprinkling those onto your S-plane to modify or adjust your system. You will learn how to position those zeros and poles to modify your system into a form that's more effective for its overall behavior. In the state space, we actually might begin that discussion with a very ideal situation and say, oh, let's just assume that we have the entire state vector available for measurement. Let's say you have a mechanical system. Maybe it's a couple of masses and some springs and dashpots. You now have a couple of positions and a couple of velocities. That's your state vector. You have 4 state variables. Position 1, position 2, velocity 1, velocity 2. In full state feedback design, we're assuming we can go in and measure each of those variables, 2 positions and 2 velocities. We'll learn how to gain those values and feed those back to adjust the system's behavior, to make it operate in the manner that we want it to move. Now we can go even more than just first order, thankfully. We will look at PID controllers, which is a controller that has a proportional piece, an integral piece, and a derivative piece. That's the P, the I, and the D. The PID is a proportional integral derivative controller, and we'll look at how do we design those to enhance our system's closed-loop performance or behavior. In the state space domain, we may not have access to the full state vector. Well, we will learn how to create a system of our own that's actually trying to duplicate what the system itself is doing, and that will be observing the original system. And what's coming out of the observer will be estimates of all of our state space variables. It'll be an estimate of position 1, an estimate of position 2, and an estimate of velocity 1, and an estimate of velocity 2. And we'll use those estimated values to control our system. Obviously, that introduces some uncertainty, and it's not the same as measuring those directly. And our performance might be a little bit different with an observer-based design versus full state feedback. And we'll learn how to think about and adjust those differences or adjust for those differences in the design. So what are we doing? In the big picture, your system actually might be, well, you've already inked that in. Sorry. In the lab, you might go in and you might actually command that mass spring damper system to move over a centimeter. You say, go a centimeter to the right. Well, it doesn't just go over there and lock in. It goes and shakes around that. And that's what I'm drawing here by this. And actually, maybe where you commanded it was up here. Because of that, you have a huge steady state error. And you go, ooh, I don't know that I like that. And maybe you don't like the way that it went beyond where it eventually ended up. Maybe you want to take some of that overshoot and get rid of it. You might also not be happy with how long it's taking before it settles to a final value. So you may want to speed up the system, you may want to minimize the overshoot, and you might want to reduce the steady state error. And some of those are conflicting, those characteristics. The steady state error and the transient behavior, you sort of have to trade off. You may have to say, well, I'll allow for it being a little slower in order that I have better steady state accuracy. But now when you go into the lab, you might actually be able to design a controller so that now this is your closed loop response versus the open loop response. And that's what we're trying to achieve in this class, is a way to model, analyze, and then design to convert the green to the red. Never mind, I won't say any more. That's all for today. We'll start Wednesday with modeling.